So I picked out four different problems for you that should give you a good handle on the material that was covered in lectures 3 and 4. And as always, quiz and problem set number 1. I had a couple of questions about this. So quiz and problem set number 1 are on the material from the material that was covered in tutorial 1. So that's lectures 1 and 2. So it's always quiz X and problem set X are on the material covered by tutorial X, where X is the same number in all of those, right? So you always know which lecture, what is the lab that has the due date. Check the target schedule. That would be lab 1. So there's 3 labs, right? Lab 1, 2, and 3. And the due dates, you've got the due dates for all 3 labs. You've got the due dates for all 3 labs and all of the problem sets and all of the quizzes all on that target schedule that I gave you. Okay. So the first of the 4 problems that I picked out is like this. So I'm just gonna put the sketch up on the board here. Okay, so what we have in this problem is we've got a pipe made of 2014 T6 aluminum, and here's the pipe portion at the end here. Hidden lines there. And that's attached to a stainless steel cylinder here, and that's fixed to a wall like this. And we've got a couple of points of load application. Point B here, where we have a load of 2.5 kilopounds kip that direction. And this distance down here is 1 foot, and this distance over here is 2 feet, and the length of the pipe here is also 2 feet. And then on the pipe, we've got an axial load, but it is a distributed load, and the magnitude of the distributed load decreases linearly, moving from point C here, where the value of that distributed load is 700 pounds for every foot length of pipe, down to a value of 0 at the end. So this is 0 pound per foot as there. So we've got a decreasing axial load applied over the length of that pipe. Okay, so let's label some other points. So we've got point B there. Point A is over here at the wall. This is point C, where we've got the junction between the solid cylinder and the pipe. And then point D we'll call the other end. We're given a couple of cross sections here. So we've got AB, section AB has a solid cross section like this that is 1 inch in diameter, and this was the, for your material property table, the 304 stainless steel. And then we've got section CD, which is the pipe, and it's got an external or an outer diameter of 1 inch and an internal diameter of 7/8 of an inch. And that is made there from 2014 T6 aluminum. 2014 T6 aluminum there. Okay. So for the first part of the problem, first of all, is my writing large enough there for everybody? You can see okay? I'm not seeing any chitter chatter about technical difficulties, so that's good. Looks fine. Okay, great. Okay, yes, go ahead. these two circles down here, those show the cross section, sorry, of these objects. So this is the cross section of segment AB, okay? And this is the cross section of CD. Okay? That makes sense? Yeah, okay. Okay, so part one, we want to determine the maximum stress in the assembly. So determine maximum stress. Okay, so let's do that first part there, determine the maximum stress. So first of all, there are all axial loads here. There's no loads in the vertical direction, neglecting weight, and we don't have density values for either of these materials. So we'll assume that the weight is negligible. So assuming that weight is negligible, right? Then we have all horizontal axial loads. So there's only going to be internal normal forces within this assembly. So we're only going to be dealing with normal stresses. So our equation for normal stress, if you remember, sigma equals n divided by a, right? And we always are calculating normal stress at a particular location. Now, we've got two different portions of the object and they have differing cross-sectional areas, right? So we're gonna probably end up having to calculate what the maximum stress is in the pipe portion and the maximum stress is in the solid portion because we've got two objects of different cross-sectional areas. But we'll see. So first of all, let's look at what the let's get our support reaction here first, maybe. So let's change this whole object to a free body diagram. There we go. And we've erased a solid connection there, so we know that there can be a vertical force at the wall, AY, a horizontal force, AX, and a moment M about A. Now, AY, we just said because we're assuming that the weight is negligible, that's going to be 0 there. And then we can get AX by doing a sum of the forces in the X direction. So let's do that. So sum of the forces in the X direction has to be 0 for the whole object. And I'm going to take over to the right as being my positive direction here. So in that equation, we've got AX subtract our 2.5 kip, and I'm changing that to pounds there. And then the other thing that we have is that we've got this distributed load. Now, when we put that distributed load into our sum of the forces equation, we want the resultant of that distributed load. Now, what this load does, again, it linearly decreases from a value of 700 pounds per foot to 0 pounds per foot over a distance of 2 feet. So if we were representing that distributed axial load on a graph of, let's say, distributed load little w over length L, then this load starts at 700, and this is in units of pounds per foot there, and it decreases to a value of 0 over a length of 2 feet. Okay, so this is in units of feet there. Now, anytime you want the resultant of a distributed load, what you need to do is you need to take the area of an area under the curve of your distributed load over length diagram. So the resultant of that distributed load is equal to that area. In other words, you integrate your equation for your distributed load over length. So area here equals resultant. And of course, this is really easy when you have triangular distributed loads because you're just calculating the area of a triangle and you don't need to do the integration. So here we have 1/2 of the base length, which is 2, multiplied by the height, which is 700 there. And that has to be equal to 0. Okay. Plus. I'm going to switch markers here and get a fresh one. Anybody have questions about that distributed load? I know that's static stuff, but just as a review of how to handle those. So this is going to give us AX here. So we've got AX, we're going to move the 2,500 over to the other side and subtract 700 from that. So we're going to get 1,800 pounds there. Okay. So that, because we came out with a positive number there, that tells us that our orientation for the distributed, or orientation for AX on the free body diagram here was correct. Okay. So now that we've got AX, we can think about sectioning our object in a couple of locations and looking for where the internal normal force is maximum. So if we section the object here between A and B, then our free body diagram looks like this, where we've got AX here, which we know now is 1,800 pounds. And then we can have an internal normal force, an internal shear force, and an internal moment M. Now, again, we know that this is 0 from sum of the forces in the y direction equals 0. So there's no internal shear force. In fact, there's no internal moment in this case, so we could get rid of that. Not that we're considering internal moments yet, but the only thing we're left with is the internal normal force. Now, the internal normal force here, this would be more appropriately labeled N subscript AB, because the normal force that we're finding is only the normal force that exists within segment AB of the solid portion of this object, right? After we go past point B, that internal normal force is going to change, and we're going to see that in a minute. Okay, so if we do sum of the forces in the x direction equals 0 here, that tells us that NAB equals 1,800 pounds there. Okay, now the internal normal force NAB, that vector is pushing in on our cut section, so that is a compressive internal normal force, so it's going to lead to a compressive normal stress. Okay, now going back to stress here, right? For this solid portion, if we're finding the maximum stress, what we want is the maximum normal force, because both AB and BC have the same cross-sectional area here. So whichever of those two sections has the higher internal normal force, that section will have the higher normal stress. So let's see what the internal normal force is in BC. So we can do a section cut like that in between B and C and consider that free body diagram instead. And I'll just get rid of that there. So doing our section cut in that location, here we go. We've got AX equals 1,800 there. And we've got our applied load at point B, which was 2.5 kip. And then here we've got NBC, the normal force in BC. Sum of the forces in the x direction needs to equal 0 for this segment as well. So what have we got? 1,800 minus 2,500 plus NBC has to be equal to 0. And that gives us NBC, take 2,500 over the other side, subtract that. That means that this is 700 pounds, right? So the normal force in BC, much lower than the normal force in AB. So which of the two locations is going to have the higher stress in the solid portion of the object? It's segment AB. So the stress in AB is going to be equal to NAB divided by the cross-sectional area of AB. And that is 1800 divided by pi over 4, and then d squared, the diameter 1 inch there. Okay. So that gives us a value of, let's see, what did I get when I did that? I got 2.3 KSI. 2.3 KSI. There we go. Now that number actually comes out in units of PSI, and I've divided by 1,000 to change it to KSI because we've got pounds and we've got inches squared on the bottom. And I see that somebody asked a question in the chat there. And the question was, let's see, since it's finding a triangular area, it's easy, no integration needed. Yes, exactly. Yeah, right on. Okay. Why do we assume that the force in the y direction is 0? So you're talking about up here, or you're talking about over here, ay equals 0? Yeah, so you're talking about this 700 pounds right there? Yeah. So that is actually not a force in the y direction. That represents, so this triangle here is just a sketch to represent how this axial load is changing with length. Okay, so this axial load, the large vector at the start represents an axial load of 700 pounds per foot, and the magnitude of that load decreases as we move along the length of the tube down to a value of 0. Okay? Yeah. No, and I'm glad you asked, because this is the first time, like, a lot of you will have seen an axial load that's changing represented in this format. So it's quite common to show decreasing vectors and then do a little sketch above to show how that load changes over distance, and in this case show that it's linear. So this little sketch up top here is exactly the same as that XY plot that I did with W versus length L and the load decreasing from 700 to 0 over a length of 2 feet. Is that what we use every time for a cross section of the cylinder? Are you talking about pi over 4d squared? Yeah. So, I mean, you're finding the area of a circle, right? So you can use pi r squared or pi over 4d squared. It doesn't matter. They're the same equation. Whatever works for you in terms of finding the area of a circle. Okay. So we've got the stress, we've got the maximum stress in the solid portion now, but we wanted overall what was the maximum stress in the object, right? So we need to know what the maximum stress is in the tube portion of the object as well, and compare that to our 2.3 KSI to actually answer the question. So what we're going to do now is look at what is the maximum internal normal force within that tube portion. Okay, so let's do a section cut just somewhere in between point C and point D there. Okay, so if we do that, then our free body diagram, if we take the right-hand side of the object, right? Whenever you're finding internal forces, you can always take one portion of the object or the other portion when you do your section cut. And it makes sense to take the portion where there's the least amount of math involved. So here we've got a couple of, we've just got a little bit of that linearly decreasing axial load present on this. So, and I'm going to represent that by just a little bit of this, this graph that was indicating how the magnitude of that load changed with length. So this will be some length L there. And the magnitude of this decreasing axial load, right, will be some magnitude h, where h is a value between 0 and 700, depending on what the length L actually is. And now the only other forces that we have left are the internal forces. And we know that the internal shear force is 0 now, and we're not worrying about the internal moment, but that's also 0. So all we have left is the internal normal force, and that's N subscript CD. Okay. So what you can see now is that when we do sum of the forces in the x direction equals 0, we have NCD is simply equal to the resultant of that distributed load, which is 1/2 of the base L multiplied by the height h, right? So where is NCD going to be greatest? Well, it's going to be greatest when L is maximized, and L is maximized when we get right to the junction between the tube portion and the solid portion. Okay, so max NCD occurs when L equals 2 feet in this expression above, right? So NCD max is equal to 1/2 of 2 multiplied by h, and when L is 2, h is 700, so we've got 700 there equals 700 pounds. Okay, so now we can find the stress associated with that. It's so nice to change markers and actually have like something super bright. Okay, so now we can find the stress associated with that. So, and sigma CD max, right, is going to be NCD max divided by the cross-sectional area, ACD, which equals what? 700 divided by, now 700, that's a lower number than 1800, right? But the cross-sectional area here is bigger than the cross-sectional area of the tube is going to be. So it's not clear whether this stress is going to end up being higher or this stress in the tube is going to end up being higher. So we have to do the calculation. So cross-sectional area now for a tube, right? You do outer area minus inner area. Pi r squared outer minus pi r squared inner, or pi over 4 outer diameter squared minus pi over 4 inner diameter squared. So we've got pi over 4 outer diameter squared 1 squared minus inner diameter 7/8 squared. Okay, there we go. Don't forget to square these numbers before you take their difference. Okay. So when I did that calculation, it gave me 3.8 KSI. So 3.8 KSI. Okay. So that's the answer to part 1 of that problem. Does anybody have a question about what I just did there? just give you a minute to process while I'm doing some cleaning up here. Okay. All right. Okay. No questions. Seeing nothing. Okay. So let's move on to part B. Okay, so what were we asked for in part B? Part 2, determine the total length change of the assembly when it's loaded. So, okay, so part 2. Determine total length change, and that means when loaded. Okay. So whenever you're given a problem like this, all of the dimensions that you're given are the unloaded dimensions of the object. Okay, these are the dimensions before these loads are actually applied. So what we want to know now is when these different loads are applied, so 2 loads here, the 2.5 kip and this distributed load, what's the total length change of this object going to be? So in other words, what we want to find is the change in length all the way from point A to point D, right? That's the question. Now, you know from the lecture that whenever you have an object where the internal normal force is changing over length, you need to do a length change as the summation of individual length changes for segments where either the normal force is constant or the normal force is changing in a continuous manner. Okay, so for this object here, what we're going to have to do is we're going to have to say that the total length change from A to D is going to be equal to the total length change from A to B plus the length change from B to C. Right? Why do we have to do those two? Well, because we already know that the internal normal force in segment AB is different than the internal normal force in BC. Right? So when the internal normal force changes, you need to sum those up. And then we've got the length change from C to D, delta L CD. And in that segment, the internal normal force is changing in a continuous manner. Okay, so let's expand these terms out. So the change in length equation is delta L is NL over AE. Right, if you've got a constant internal normal force. So it's easy to apply that equation to these components because all you do is take all of the individual variables here and add the subscript AB on. So the length change of AB is going to be equal to the normal force in AB multiplied by the length of segment AB divided by the cross-sectional area of AB and the modulus, it's a bit messy, the cross-sectional area AB and the modulus of elasticity of segment AB. Okay, and then we add on the same thing for segment BC. So we've got the normal force in BC, length of BC, cross-sectional area of BC, modulus of elasticity of BC. Okay, plus. Now for this segment here, this is one where the internal normal force is changing continuously with L, so we need to use the integral form of that equation, which is the integral from 0 to L of N, and this would be N here CD where NCD is an equation that describes how the internal normal force NCD is varying with length L. And then we've got DL, and then we've got ACD, ECD down there. Okay. All right, so after we've got this equation done, you've really demonstrated that you understand a large portion of how the problem needs to be completed. So now it's just a case of taking care of the details, right? So let's just go back and look at what the internal normal forces were again. So I'm going to just erase this stuff down here for a second and draw those section cuts just very quickly again on the glass here so that we have them to refer to, okay? So this one was 1800 here, and then we had NAB here, which was 1800, and then we had another section cut already done over here. And we said that this was 1800, and then we've got 2500 in this direction, which leaves us with NBC is 700 in that direction. And then we had another section cut that we'd already taken over here, right? And we've got this section here where we said that this was length L long, this was some height H there. These are our decreasing axial load vectors going that way, and we've got N, C, D there, okay? And we said NCD was going to be equal to 1/2 base times height LH, okay? So now we're in a position to fill everything in, and I'm just going to move that equal sign over to the left there to give myself some extra space. Who's ever got the notifications that keep buzzing? Do you mind muting yourself? That would be great. Okay. Any questions before I go on and start adding numbers into this equation here? Okay, not seeing any, so I'll continue. Okay, so the normal force AB. Here's the normal force AB up here. It's 1800, but it's a compressive internal normal force, and the rule when you're doing change of length using superposition by adding things up is that you have to pay attention to whether the internal normal force is compressive or tensile. And if it's compressive, you make it a negative sign when you put it into the equation here, right? Because if you've got some internal forces that are compressive, some internal forces that are tensile, some segments are getting shorter, some segments are getting longer, and you have to add and subtract those appropriately. So we've got minus 1800 down here, the length of segment AB. So that is just the length between A and B, which is 2 feet. Now, remember, when you're using equations that involve stress or things that are related to stress, like modulus of elasticity, you want all of your numbers to be in pounds, inches, PSI when they go into this type of equation here. So I'm going to take that 2 feet and I'm going to multiply it by 12 to change the feet to inches. Okay. Now we've got on the denominator, we've got the area of segment AB. That was pi over 4d squared, where a diameter is 1 inch. And then we've got the modulus of elasticity of segment AB, right? So the solid portion is made of 304 stainless steel. So if you flip to your material property table, make sure that you're in the US unit side. Look for 304 stainless steel. You'll find that its modulus of elasticity is 28 times 10 to the 3 KSI. So that means this number has to be 28 times 10 to the 6 PSI. Okay? Plus, now our normal force NBC goes in. That's 700. It's tensile. Why? Because it's pulling the cut section away from itself, right? It's pulling out on the rest of the object. So we've got 700 here, length BC. Now, don't be confused and look at this free body diagram here and think that, oh, if I take this section cut over to point C here, that free body diagram is going to be 3 feet long. That's true, but LBC is only the length of segment BC, which is 1 foot. So you need 1 here, and you need to multiply that by 12 to change it to inches. Then cross-sectional area, it's exactly the same, the denominator exactly the same as we just had. So pi over 4, 1 squared, 28 times 10 to the 3 KSI, which is 28 times 10 to the 6 PSI. Now we've got the integral from 0 to length L, where L is the maximum length that this expression for NCD is good for, right? So that's all the way from this end of the pipe here to the other end. That's 2 feet. So 2 up here as our limit on our integral. Again, don't forget to change it to inches. Multiply by 12. Our expression for NCD, we've got that expression right here, but having a variable h in that expression is going to do us no good at all, because then we won't be able to carry out the integration, okay? So we need to get rid of that variable h. That is easy to do, right? Because here's h right up there, and we see that this triangle here that I'm shading in has the same angle as the larger triangle. And that means that the ratio of A to B here has to be equal to the ratio of 2 to 700. So the base to the height of the small triangle has to be the same ratio as base to the height of the big triangle. So we can write an expression relating that. We can say that h, which is the height b, over the length a, which we defined as variable L, right? That variable is right down here, is equal to 700 over 2. Okay? 700 over 2. Okay. All right. Now, let's remember here that our L is in inches here. Okay. So let's change everything else to inches. So we can multiply 2 by 12 to change that to inches, and take the 1 foot that's under here, 700 pounds per foot, and change that to inches there. Okay. So then what have we got? We've got h equals 700 divided by 2 times 12 squared multiplied by L. Okay. So that h there can come down here and into our expression right there. Okay, and that's going to go in for NCD. Now, NCD is tensile, so that whole expression is going to go into the integral sign as a positive. So we've got 1/2 L, and then our value of h here, 700 divided by 2 times 12 squared multiplied by another L dl. Okay. And then we can put this all into our calculator and hit solve and get a number for what the length change is. Okay, where did the 12 come from? Looking at the chat here, where did the 12 come from? Yes, changing feet to inches, exactly. Okay. So when I went through and did that, what did I get? I got 0.001288 inches. So what I said? Yeah, 1288 inches. Now that comes out as a positive number. So what does it mean that it came out as a positive number? We were taking internal normal forces that were tensile as being positive. So that means that this number that we got out, that's an elongation. So when the loads are applied, the whole thing elongates by 0.00128 inches. Yes. Yep. Oh, thank you. Thank you very much. Yeah. Good, good. We missed this term down there. We didn't miss it. I shouldn't use the we. I missed writing that term down there. So that needs to be on the denominator. And of course that can come out of the integral sign if you want with all the rest of the constant values here. But that should be pi over 4 and then the outer diameter squared minus the inner diameter squared. Okay. And then we need to multiply by the modulus of elasticity. And that's the modulus of elasticity for 2014 T6 aluminum. So if you flip to your material property table and locate 2014 T6 aluminum, it's right up near the top. Two grades of aluminum on that material property table, 6061 T6 and 2014 T6. It's 10.6 times 10 to the 3 KSI. So we've got 10.6 times 10 to the 6 PSI. Okay, thank you very much for pointing out that I had missed that. That's great. Okay. Anybody else have other questions about that problem there? So it's a good problem for practicing whether or not you know how to do axial deformation using superposition, right? Because you've got the integral component of it there. You've got a couple of portions that have constant internal normal forces. So good practice. This one here. Yep. So that again, that 2 is this length here, right? Because that expression for NB or NCD here is valid for the entire length of the tube, which is 2 feet. And again, we're taking the 2 and we're multiplying it by 12 to change it into inches. So we're integrating over 24 inches. Yep, no problem. Why do you have L twice in the integral? That's a good question, right? So remember the expression for NCD started down here, where NCD, and this was from sum of the forces in the x direction equals 0, right? We got NCD has to be equal to the area of that little triangle. And the area of that little triangle is 1/2 L times H. L being whatever distance or length this free body diagram is, and H being whatever height that is. And then we said, okay, we have to substitute in for H. So what is H? So this is where we used similar triangles to substitute in for H, where this is H, this is L there. The whole base length of that triangle we know is 2 feet, and the whole height we know is 700 pounds per foot. So we said that height of the whole triangle, 700, divided by its whole base, 2 feet, has to be equal to height of the smaller triangle within it, h, divided by its base length, L. Why? Because they both share this same angle, alpha. And that means that tan alpha has to be equal to 700 over 2, and also has to be equal to h over L. Right? And then we just changed the 700 pounds per foot into pounds per inch by dividing by 12, and the 2 from feet into inches by multiplying by 12. So that's where that 12 came from, as well as that 12 came from up there. No problem. All great questions. Okay. Not seeing any other questions, so I'm going to do some erasing here, and we'll move on to problem number 2. Okay, so problem number 2. Let's see what we've got. Okay, there it is. So in problem number 2, we've got a setup that is like this. Okay, where we've got a horizontal rigid bar here that is pinned to a wall, and we have a cable hanging down like this with a load of F being applied to it, and it's supported by another cable over here going up to another support there. And let me put some numbers on here. So the length of this cable is 3 meters. This is going to be point A there. This is going to be point B there. Point C here, point D at the end of that other cable. And let's make this point E over here. The length of this cable is going to be 2 meters. And this distance between those two cables, 1.5 meters. And this distance, point E, is going to be 3 meters. Okay. Okay, so 2 stainless 304 steel cables. So these cables are both 304 stainless steel. Support a beam, right? Cable AB has a diameter of 8 millimeters. So diameter of AB equals 8 millimeters there. And cable CD has a diameter of 10 millimeters. So CD is 10 millimeters. If the cables must have a minimum safety factor of 2.5, so I'm going to write that down. Our safety factor, our minimum safety factor is 2.5. Determine the maximum allowable load F that can be applied. Right, there's F. Rounded to the nearest 100 newtons. F max is the question, and we're told to round to 100 newtons. Round to the nearest 100 newtons. Okay, great. All right. So we've got 2 cables here. The loads will be different in them, and they're also different diameters. If we've got a safety factor of 2.5, right? What that is saying is that we're going to allow the maximum stress inside the cable, and I'm writing normal stress here because cables can only carry tensile loads, so they must be under normal stress. So what we're saying here is we're going to allow the maximum stress in these cables to reach the yield strength divided by the safety factor. So we're going to allow them to go up to a fraction of their yield strength to allow a margin of safety here. So if I look at 304 stainless steel in the metric portion of the table and look for the yield strength, you will see that it is 207 megapascals. Okay, so sigma Y for 304 stainless steel is 207 megapascals. Okay. So we're going to let the maximum stress then go up to 207 megapascals divided by 2.5 for our safety factor, right? So that's going to be our maximum stress. So what we need to do is to find what the maximum stress is in these two cables and equate it to that side of the equation. So if we flip this around, we're going to say that 207 divided by 2.5, we're going to set equal to our maximum stress. And what is our maximum stress? Well, it's going to be the normal force in each cable divided by its cross-sectional area. And if we have normal force as a function of our unknown load F, then we can solve the problem. So what we need is our normal force N in each of these cables as some sort of function of our applied load F. Now, this is really easy for cable CD, right? Because if we take a section cut through cable CD, then what do we have for a free body diagram? We have load F here, and then we have our normal force in CD, which must be equal to load F, because we know that some of the forces in the Y direction has to be equal to 0. Okay? Again, neglecting the weight of the cable itself. So let's put that into this expression and see what we get for load F, and then we can do a similar consideration for cable AB. Okay, so for cable CD, we've got 207, and now I'm going to change this from megapascals into pascals times 10 to the 6th there, divided by 2.5 is equal to the normal force in CD, which is load F, divided by the cross-sectional area of CD, which is pi divided by 4 times the diameter squared. 10 millimeters is 0.01 meters squared. So this gives me F for cable CD. So let's see what that comes out to. Okay. Now that is not a value I actually solved for when I did the problem, so we'll just quickly do it. So I've got 207 times 10 to the 6 divided by 2.5 times pi divided by 4 multiplied by 0.01 squared gives us 6.5, and that is actually, it comes out to 6,503, right? And this is in units of newtons. So we'll leave that unrounded for the moment, because then we can talk about it. Any questions up to this point here? Okay. Should 207 be converted to pascals? Yes, exactly. Yeah, so I did that. So I wasn't doing that here, but yes, when you actually put in the numbers, you should do that. Yeah. Okay. Everything, when you're working in metric and you've got equations involving stress, you want newtons, meters, pascals as your units there. Okay, now this doesn't necessarily mean that F can go up to 6,500, because by the time F reaches 6,500, the stress in cable AB might have exceeded the maximum allowable stress. So we also need to check what the maximum F would be for cable AB. So the easiest thing to do here is, first of all, well, not the easiest thing to do, the thing that you have to do is you need to figure out what the internal normal force in cable AB is in terms of load F, and the easiest way to do that is to draw a free body diagram of this horizontal bar there. So if we draw a free body diagram of the horizontal bar, we've got EY and EX for the pin, and then we've got F AB for the force being applied from cable AB to this bar, and then we've got load F here, which is the force that cable CD is applying at point C. Okay. And now what we can do is simply do a sum of the moments about point E has to be equal to 0. And that gets rid of E, Y, and EX here. So doing this, we've got the moment created by force F has to be balanced by the load created by FAB. So F multiplied by its moment arm, which is 3 meters, has to be equal to FAB multiplied by its moment arm, which is 4.5 meters, 4.5. Okay. So we've got FAB is equal to 3 over 4.5 multiplied by load F there. Okay. So now we can we know what the internal, or we know what the load FAB is, and the load FAB, that's the load that is also applied on cable AB. So if we draw cable AB now, here's A, here's B, then if FAB is upwards in this diagram, FAB is downwards in this diagram, and then if we do a section cut through the cable, we see that the internal normal force is equal to FAB there. Right, so now we can do the exact same thing we did for cable CD, but for cable AB, using this as the internal normal force. So we've got 207 times 10 to the 6 divided by 2.5 is equal to our internal normal force in cable AB, which is 3 over 4.5 multiplied by our applied load F divided by our cross-sectional area, which for this cable, it's an 8 millimeter diameter cable. So we have pi over 4, 0.008 squared. Okay, and that gives us a value of F. Now, let's just take a second and do that calculation. So we've got 207 times 10 to the 6 multiplied by pi multiplied by 0.008 squared divided by 2.5 times 4 there times 3 divided by 4.5. Okay, and that gave me when I did it, 6,243 newtons. Okay. Okay, so then what is the maximum load that we can apply? What's the maximum load F? Well, the maximum load F that we can apply would be the smaller of these two, right? Because if we go up to the larger value, then cable AB will have exceeded its maximum allowable stress, or in other words, its safety factor will be lower than 2.5, which isn't allowed by the design. So the maximum allowable load has to be the lower one. Now, in terms of rounding to the nearest 100, right, we'd have to round this number down regardless of whether it was closer to 6,200 or 6,300, okay? Because rounding it up to 6,300, let's say it was 6,283, rounding it up to 6,300 would make our safety factor smaller than 2.5, which we're not allowed to do because that's the minimum allowable safety factor, okay? So therefore, F max is equal to 6,200 newtons or 6.2 kilonewtons. Okay. Questions about anything from that? There's a second part of the problem here. But we'll entertain questions about the first part if anybody has them. Oh, this guy here, like right here, this down here. Guide me left, right, up, down. Finger with the marker is close. This one. Yes, okay, great. Good directions. So this is here. I'm just saying that if we look at this doodle here at the top, and I'm just calling it a doodle since I haven't put the 207 in the proper units by raising it to the 10 to the 6, but just this conceptual idea of what we're doing here. In order to solve the problem, what I was saying is that we need N for each of these cables, the internal normal force, but we want the internal normal force as a function of variable F. So that's just F for function here of variable F. Right, we want N as a function of F, which is exactly what we've got over here, and which is actually what we've got over here. We've got N as a function of F right here as well. It turns out to be a function that is not a very complex function, just being a constant, but a function nonetheless. Okay, I'm going to check the chat here. Nothing else in there. Okay, so let's move on to the second part of the problem then. Yes. Yep. Yeah. Well, and that's a great question. That would be absolutely true if these two cables had the same diameter, right? But because they're differing diameters, if this cable had been a fraction bigger then the other cable would have been the limiting factor, right? Yeah. But you're absolutely right. If they were equal diameters, which would be the case if you were actually designing something like this, but they aren't equal diameters, exactly so that I can answer your question and make that point. So I'm so glad you asked that. Yep. Okay, so for the second part of the problem here, what we want is, let's see, when the maximum load calculated above, which was, I'll just put this up so we don't lose it, that was 6.2 kilonewtons. When the maximum load calculated above is applied, what is the vertical displacement of point D? So here's point D. So we want the change in vertical position, delta y, of point D. Okay. All right. So when F is 6.2 kilonewtons, what is the vertical displacement of point D? Okay, so let's think about this. When F is applied, what's going to happen? Cable CD is going to elongate, right? That's going to move point D downwards. But cable AB is also going to elongate, and that is going to cause this bar to rotate, which is going to move point C downward. And that downward displacement of point C is also going to contribute to the displacement of point D. So looking at just quickly here, the original, if I just draw this as a line diagram here, we've got B and we've got point C there. When this thing deforms, it's going to go from being like that to being something like that, where point C is now down here, C prime, let's say, and point B is down here, B prime. This length change here is going to be, that was supposed to be a delta, not an A. That is going to be whatever the change in length of cable AB is, okay? This distance here is just the change in position, delta y, of point C. And then we've got here the cable CD, and then that's going to change in position a little bit here. So that length change is delta L of CD. So the change in vertical position, delta y, of point D is going to be equal to the change in position of point Y, or point C, change in position of point C, plus the elongation of LCD, okay? Now, delta LCD, right? That's really easy to get because that's just the axial deformation equation applied to that cable. So simple. The change in position, delta YC, that's also pretty easy, right? Because we can relate that to the change in length, delta AB, because again, we've got a situation where we've got similar triangles here. We know that this distance here is, what, 3 meters, and we know that the overall base length here is 4.5. So we can say that delta YC over 3 is equal to delta LAB over the total base length, which is 4.5, right? So now we've got an expression, delta YC is the change in length of AB multiplied by 3 over 4.5. Okay, so we can substitute that in right down here and say that 3 over 4.5, make that a bit nicer, 3 over 4.5 delta LAB plus delta LCD is going to give us the total change in the y position of point D. So now we just need to calculate these two axial deformations. So let's expand those equations out. So we've got 3 over 4.5. The change in length of LAB is going to be the normal force in AB multiplied by the length of AB divided by its cross-sectional area of AB, and its modulus of elasticity E. Now I'm going to drop the subscript there just because both cables are made of the same material, so we don't really need a subscript there. And then for LCD here, we've got NCD, LCD over cross-sectional area, CD, and again, modulus of elasticity. Okay. So let's put in some numbers and complete the problem. So we've got our 3 over 4.5. Now I'm just going to check if there's questions before I move along, and there's not. So NAB, right? We said NAB was what? 3 over 4.5 of F from the last problem. We said NAB is going to be 3 over 4.5 of whatever load F is. So I'm going to pop that into here. So we've got 3 over 4.5 of load F, and I'm not going to put F in, of course. I'm going to put what F is in there. So we've got 6,200. And then we've got the length of AB, which is 3 meters. And then we've got the cross-sectional area down on the denominator here. Let's save some space and put it there. Cross-sectional area, pi divided by 4. And it's an 8 millimeter cable, 0.008, square that. And then we've got modulus of elasticity. So we're talking about 304 stainless steel in our metric units. And that is going to be 193 gigapascals. So we've got 193 gigapascals. That's times 10 to the 9 there. Okay, and now we've got a second term to add on. So plus NCD, right? The internal normal force in NCD is load F, and that's 6,200. LCD, 2 meters for that cable length, divided by cross-sectional area for CD, pi over 4, and we've got our diameter of that cable is 10.01 squared, and then same material, 193, not 2, times 10 to the 9. Okay. So huge numbers down in the denominator here, times 10 to the 9, right? So we're going to end up with a small number for the answer on this one. And just how small is it? It is going to come out of this equation in millimeters, 1.6, or it's going to come out of this equation in meters, sorry, multiply by 1,000 to change it to units of millimeters. So you get 1.67 millimeters after you multiply by 1,000. Okay. How's the speed of this for people? Am I moving too quickly? It's always a balancing act of keeping things quick enough so people don't fall asleep and not making them so quick so that you can't take notes while we're going. It's fine for me. Okay. Okay, great. Is it too slow? Do I need to speed up? No, okay, okay, good. I was gonna say I can totally have another coffee and do that, but if I don't need to, that's fine with me too. I'll stay with the sparkling water. Okay, let's move along then to the third problem. Dun, 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 dun. So I figured out the audio thing from last week. So the problem with the audio last week was that because I'm running audio through both Zoom and QuickTime, the two programs, pieces of software, did not like sharing a common audio signal. So you can't see it today, but I've got my AirPods in, which I'm using for Zoom, but then I've got a microphone mounted to the ceiling, which I'm using to capture the audio for the QuickTime recording. So everything was good there. It only required me to buy a new USB-C cable. So easy fix. Okay, so let's keep going. Oh yeah, this is a short problem, which is nice to have a short problem after those two other ones, but it's an important one too. So what we've got here is we've got a steel tube that's like this. Okay, there's a steel tube, so it's going to be an A36 steel tube. And what do we have? We've got an outer diameter of 70, what's that, centimeters, and an inner diameter of 60 centimeters. Here, outer diameter 70 centimeters, inner diameter 60 centimeters. And into that steel tube, this is on the ground, into that steel tube, we pour concrete. So we've got concrete on the inside. Okay, and that is going to be high strength concrete. If you look at the material property, I paused there because if you look at the material property table, there's high strength concrete and medium strength concrete. And I knew we needed to know which of those it was, but it's high strength. Okay, so I'll read the problem statement here. It says, a column is made by pouring high strength concrete into an A36 steel tube with an outer diameter of 70 centimeters, inner diameter of 60 centimeters. The concrete and steel are well bonded when the concrete dries, so there is no slip between the two materials when they are loaded. That's a key sentence there, right? The concrete and the steel are well bonded when the concrete dries, so there is no slip between the two materials when they are loaded, right? So there's no slip between the concrete and the steel when they're loaded. So the whole column, in other words, deforms as one solid piece. Okay. So when this load F is applied, that's applied to the top of the column, that means that whatever the length change is, and we know that when a compressive load is applied to something, that thing will get shorter. So when this compressive load is applied, the steel will get a little bit shorter, the concrete will get a little bit shorter, but the change in length will be the same for both of them. Okay. What is the maximum load F that the column can carry for a safety factor of 3.5? So F max for a safety factor of 3.5 is the question that we want to answer. Okay. All right. So what do we need to think about here? So again, we've got a safety factor involved. So we know we're going to allow the stress to go up to some maximal level. So for the steel, right, with a safety factor of 3.5, the maximum stress that we're going to allow the steel to reach would be its yield strength divided by the safety factor. Okay, the yield strength divided by the safety factor. For the concrete, right, the maximum stress that we're going to allow the concrete to reach would be not its yield strength, right? Because concrete doesn't have a yield strength. It would be its ultimate strength, and in particular, its ultimate strength in compression, or its compressive ultimate strength. So sigma u compressive divided by its safety factor, okay? Where the safety factor in both of these equations would be our design safety factor 3.5. Now, it's much the same as the previous problem in that we've got the variables in this side of the equation. Like for steel, we have the yield strength from the material property tables. We've got the safety factor, that's 3.5. We've got the ultimate compressive strength from the material property table. We have the safety factor. So what we need to equate these two then is the normal force in the steel divided by the cross-sectional area of the steel. So we're setting maximum stress equal to maximum stress. And then for concrete, again, the normal or the internal normal force in the concrete divided by the safety factor. Okay. So what we need is expressions that give us the internal normal force in the two materials in terms of our unknown load F. All right. So we can get those by doing a section cut through the object, right? So let's draw a section cut through the object, okay? Here's, actually, I'm going to draw that a little bit lower. So there's the section cut, and the rest of the column is up here. And I'll draw like a cross-sectioned drawing of it here. So we've got the steel on the outside and the concrete on the inside here. And we've got load F being applied. And what do we have in the free body diagram now? We've got our externally applied loads. Don't know anything about the density of materials, so we're going to assume weight's negligible. But then for our internal loads, right? For our internal loads, there'll be some normal force in the concrete, and there'll be some normal force in the steel. That should be N subscript S. Okay. Now, I'm only drawing one vector N subscript S because really the normal force in the steel exists all the way around 360 degrees in the steel tube that we've cut, right? So I won't draw another one over here and then confuse you into thinking that there's two normal stresses in the steel. Really, this is just one normal stress in the steel, the resultant normal stress for the whole section cut 360 degrees around. So from yeah, absolutely. Yeah. Exactly. So what we've got here when we do sum of the forces equals y is we've got the applied load F has to be equal to the normal force in the steel plus the normal force in the concrete, right? But there's from just this equation, there is no way to determine what proportion of F goes into NS and what proportion of F goes into NC. So how that load F is split between the two materials, we can't tell from this equation. So this is a problem that's called statically indeterminate because you cannot determine what the internal normal forces are from the equations of statics alone. You need a second equation to help you do that. And that second equation comes from considering how the object deforms when load F is applied, right? So we know that when load F is applied, and I'll draw the sort of the same thing here. So this is the base there, and this is load F. We know when load F is applied, this whole thing will get shorter by some amount delta L, and that delta L is going to be the same for the steel as it is for the concrete. So delta L equals delta LS, the change in length of the steel. That also equals delta LC, the change in length of the concrete. And we can use this fact that delta LS equals delta LC to develop a second equation that we can then solve simultaneously with this equation and figure out what proportion of F goes into NS and NC. Okay? So let's do that. Let's expand this out here. So change in length of the steel is going to be the normal force in the steel. Again, this is just using our change in length is NL over AE equation here. The change in length of the steel is going to be the normal force in the steel multiplied by the length of the steel. Now, the length of the steel and the length of the concrete are the same, and I'm just going to call them variable L here. I'm not going to put subscripts because they're the same for both materials. And then we divide by the cross-sectional area of the steel. So we've got pi over 4, and then we've got the outer diameter, which is 0.7 squared minus the inner diameter, which is 0.6 squared. And then we've got the modulus of elasticity for the steel. And if we go to our material properties table, we're looking in metric. This is A36 steel. Modulus of elasticity for A36 steel is 200 gigapascals. So we've got 200 times 10 to the 9 there. Then equate this with the other side, delta L C. So change in length for the concrete is going to be the normal force in the concrete, NC. The length of the concrete, which we're just calling L. Cross-sectional area, pi over 4. The diameter, so if the inner diameter of the steel is 60 centimeters, that's going to be the diameter of the concrete. So you've got 0.6 squared. And then the modulus of elasticity for high-strength concrete from the table is 30 gigapascals. So we've got 30 times 10 to the 9. Okay, and now we can do some crossing out or canceling out. We can get rid of those, and the pesky pi over 4s here, and also the 10 to the 9s we can get rid of. And what we have now is we've got one equation down here, and we've got one equation up here, and we can write that solving 1 and 2 together, we get expressions for NS and NC that are in terms of variable F here, our applied load. And those equations, let me see what they come out to be, or the split between those. So we get NC is going to be 0.293 F, and NS is 0.707 F. So the steel carries approximately 70% of that applied load, and the concrete carries approximately 30% of that applied load. And the rule of thumb, when you have two materials in parallel, both carrying some applied force, is that the stiffest member takes the most load. Stiffest meaning the one with the higher modulus of elasticity. And you can see the modulus of elasticity for steel, 200 gigapascals, is an order of magnitude higher than the modulus of elasticity for concrete, 30 gigapascals. So because the steel is considerably stiffer, it takes more of the load than the concrete, right? You can think of the same thing if you hold a metal wire and an elastic band together and you try and pull them both, then your pull is going to be mostly resisted by the metal wire and not the elastic band. The elastic band is going to take very little of those load. That load. Same basic thing. Okay, so now that we've got those expressions, we can continue with applying those in these two expressions above. Okay, and then solve the problem. So let's do that. Okay, so for the steel, first of all. Okay, we're going to say that the yield strength for the steel divided by its safety factor, we're going to let equal the normal stress in the steel, which is the normal force in the steel divided by the cross-sectional area of the steel. Taking that down to the next line here, the yield strength for A36 steel is 250 megapascals. So we've got 250 times 10 to the 6. That's from the material property table. Divided by our safety factor of 3.5 is equal to the normal force in the steel is 0.707 F divided by the cross-sectional area of the steel, which was this expression over here. Pi over 4 outer diameter 0.7 squared minus inner diameter 0.6 squared. Okay, and then we get a value of F for that there. So that would be the maximum force that the steel could, the maximum load F that could be applied to the column before the steel exceeds its allowable stress. So that comes out to 10.3 times 10 to the 6 newtons. Okay, and then let's do the same thing for the concrete. Okay. So for the concrete, okay, we are going to say that the ultimate compressive strength divided by the safety factor, we're going to equate to the actual stress in the concrete, which is the normal force in the concrete divided by the cross-sectional area of the concrete. So let's put some numbers in there. The ultimate compressive strength of high strength concrete is 40 megapascals. So we've got a 40 times 10 to the 6 here divided by our safety factor, which is 3.5, is equal to NC, which was 0.293 F divided by the area pi over 4, 0.6 squared. And then we get another value of F from doing that. And that gives us 11 times 10 to the 6 newtons. Okay, so 11 times 10 to the 6 newtons, 11 meganewtons here, 10.3 meganewtons there, 10.3 meganewtons. Which one is the maximum load that can be applied to the column? Well, it's the smaller one, right? Because if we applied the larger value, then the steel would not have a safety factor of 3.5 anymore. It might have a safety factor of 3.0, which isn't allowed if our design safety factor is 3.5. Okay, so the smaller of the two values is the correct answer. So that takes us to the end of that third problem. Does anybody have a question about that? So we're going to run into quite a few of these problems that involve what's called compatibility criteria, where something is not able to be solved by statics alone. So you need to build up a second equation by considering deformations and then solve a system of simultaneous equations to get the internal loads or internal torques when we get into torsion. Okay, not hearing any questions. So let's do the fourth and final problem for today's tutorial. Okay, what have we got for the fourth problem here? What did I choose? Okay. Oh, this is a good one. Okay, so we've got, this is quite similar in setup to the second problem in some ways, but it's quite a different problem. So we've got a horizontal bar here that's pinned on this side, right there. And it's got two cables here of equal length. One going up like this to a support and another over here going up to another support, and they are each a length of 18 feet long and separated by a distance of 12 feet, and the first one here from the pin is a distance of 16 feet, like that. And then we've got a distributed load that's applied to this. Actually, it goes right to the end here. This distance is 2 feet. A distributed load. And it's a constant distributed load, so it's not changing in value, and it's got a constant magnitude of 1,100 pounds for every foot length of that bar. Okay, so the problem statement reads, the design called for two 7/8 inch diameter A36 steel cables, which would have provided a safety factor of 2.0, which was the design requirement. During construction of this, only one steel cable was delivered. So in place of the second steel cable, a cable of equal diameter, 7/8 of an inch, but made of 2014 T6 aluminum was used. This was assumed to be an acceptable design alteration because 2014 T6 aluminum is stronger than A36 steel, which was the material originally called for, right? It's got a greater yield strength, and you can check the material property tables. That's true. 2014 T6 aluminum has a significantly greater yield stress than A36 steel. The aluminum cable was placed in position CD, which isn't going to mean anything to you until I put labels on here. So A, B, C, up here, D. So CD ends up being 2014 T6 aluminum, and it's a 7/8 inch diameter cable. And AB is an A36 steel cable, also 7/8 of an inch diameter. Okay, so that's the substitution that was made. With one steel cable and one aluminum cable, is the design actually safe? Okay, so that's the simple question. Is the design safe? Okay, and just to remind you, the original safety factor was 2.0. Okay. So the question of is the design safe? What we're actually being asked there is, with the aluminum cable in CD and the steel cable in AB, is the safety factor, when the load applied is there, is the actual safety factor 2.0 or greater, or is the safety factor less than 2.0? If the safety factor is actually less than 2.0, then the design is not safe because it's not meeting the design safety factor. Okay, so is the safety factor greater than or equal to 2.0? If yes, then we're under a condition where the design is actually safe. So what we need to do is we need to determine what the safety factor is of the two cables. So for cable AB, for example, what we'll say is that the allowable stress in cable AB is the yield strength of that material divided by the actual safety factor, and we'll set that equal to the normal force in cable AB divided by the cross-sectional area of AB. And then we'll solve for the safety factor, right? Here, the yield strength for AB will be the yield strength of A36 steel. And then we'll do the same thing for CD, right? And then for CD, we'll do the same thing. So we'll solve for the safety factor here. So for CD, we'll do the yield strength, but this will be for the aluminum divided by the safety factor. And we'll set this equal to NCD divided by the area of CD. And again, solve for the safety factor. And if either of those safety factors are below 2.0, then the design is not safe. Okay. So the real name of the game here, after you've gone through that intellectual process, is just to find what the normal forces are in those two different cables. Okay. So in order to find the normal forces in those two cables, it would help to draw a free body diagram of that horizontal member. Okay. So here we go. We've got the pinned point, A, B, C, D. Let's call that point E there. So we've got EX here, EY. We've got our distributed load. Okay, we know the value of this, 1,100 pounds per foot. And we've got two forces being applied. We've got FB, or FAB, let's say, and FCD. Okay. Now, FAB here, if we look at cable AB, whatever FAB is here, then that is the force that's being applied from the bar to the cable. Here we've got the force from the cable to the bar, and here we've got the bar to the cable, equal and opposite. And that means that when we take a section cut through AB, right, FAB is actually the normal force in AB here, right? So really, by analyzing the free body diagram here, we can actually set this equal to the normal force in AB, and this similarly the normal force in CD, and work in terms of normal forces, which is actually what we want in the equations anyway. So let's do a summation of the moments around point E for the object that's shown above there. So what have we got? In the positive direction, we've got the moments from these two cables here. So we've got NAB multiplied by its moment arm, which is 16 feet here. And then we've got the moment from CD. So we've got NCD, and its moment arm is 16, 26, 28 feet. And then we've got the distributed load in the other direction. So the resultant of the distributed load is the area inside the distributed load again, just like the triangular ones. So we've got 1100 multiplied by the total length here, which is, what, 30 feet? And then that distributed load, the resultant, is going to be located at the very center, right? Which is going to be 15 feet away from point E. So we've got 15 there, and that all equals 0. So that gives us, again, that gives us just one equation, because we've got one equation, two unknowns. We don't know how that distributed load is split between those two cables based on this equation, right? And there's nowhere else we can go with this, because if we write a sum of the equations in the, or sum of the forces in the y direction, we introduce another variable, EY. So writing another equation and adding another variable doesn't help us solve this. So we need to think about what else we can do. So the other thing that we can do in this case is, again, recognize that the deformation between these two cables is going to be related because they are both attached to this rigid bar. So when this bar deforms, if I just draw it as, again, a line sort of diagram through the center here, and maybe I'll move that point over a bit to space them out. We've got point B there, and we've got point, not point C, but point D over there. When our load's applied, this bar is going to rotate about point E and be down like this. This distance here, that is going to be whatever the change in length of cable CD is. So this is change in length of CD. And this here, similarly, is going to be, actually I shouldn't draw it on that side, I should bring it down here. This is change delta L of AB. Okay? So we can relate these two quantities, again, through similar triangles. So similar triangles is kind of turning out to be the theme of today's tutorial, it seems. So we've got 16 feet here, and this whole distance from point E to point D is 28 feet. So we can say that delta L CD over a length of 28 feet is equal to delta LAB over a length of 16 feet, right? And now we can use that to build up a second equation that's also going to have the variables of internal normal force by using our equation for axial deformation to expand this, okay? So bringing this over here, we can say that I'll move the 16 to the other side here. So we've got 16 over 28 multiplied by LCD. What's LCD? LCD is NCD. LCD, or delta LCD, is NCD. LCD over ACD and ECD equals delta LAB, which is NAB, LAB over the cross-sectional area, AAB, and E4AB as well. Okay. Now, both of these cables are 7/8 of an inch in diameter. So really, I don't need subscripts on the cross-sectional areas here because they're both the same. And this also means I can cross them off. And they're actually both 18 feet long. So they have the same value of L here. So I can get rid of that as well. Okay, now we're really getting somewhere. So all we need to do is substitute in the moduli of elasticity for the two materials. And then we've got a second equation that has both the normal force in AB and the normal force in CD. Two equations, two unknowns, we can solve that. So let's bring it down to the next line. 28 equals NCD, or not equals, multiplied by NCD divided by the modulus of elasticity for CD, which is the 2014 T6 aluminum. Again, be careful, we're in the US side of the material properties table now. So 2014 T6, that's 10.6 times 10 to the 3 KSI. So we've got 10.6 times 10 to the 6 PSI equals the normal force NAB, okay, divided by modulus of elasticity EAB, and material AB is the A36 steel. Looking on the material property tables, you will see that that is 29 times 10 to the 3 KSI. So we've got 29 times 10 to the 6 PSI. And more cancellations. The times 10 to the 6s can go. Right, so now we've got a second equation. There we go. Okay, perfect. So leave the two equations up on the board here. And what we can say is that solving 1 and 2 gives us the following. NAB equals NCD equals. If you don't have a, if you haven't purchased yourself a nice graphing calculator yet, I would advise that you do that, because you will use it all the way through your engineering degree, unless you're just doing the diploma, and then not continuing. But if you're doing the full B-Eng, a graphing calculator is well worth your while. In a lot of engineering courses that you do, you know, if it's not a math course, we don't need to see the math, right? We just need to see the equations and then the solutions. So being able to plug equations in simultaneous systems of equations and then just hit solve is a very nice thing to be able to do in terms of saving time and doing integrals and all that stuff. Okay. So let's see what we get when we, or what I got when I solved those two equations together. So I got from those that NAB will be equal to 14.6 kip, and CD will be 9.3 KIP. Okay, so now that we have those, now we can go about actually checking the safety factors. So let's do the steel cable first. So now we need to check our safety factor for cable AB. Okay, so what we're doing again is we're equating the yield strength for the A36 steel divided by the safety factor, which we're looking for, to the stress that's actually present in the cable, which is going to be given by the normal force divided by the cross-sectional area. Okay, so if we do that, the yield strength for A36 steel in US units is always easy to remember, because that's why A36 steel is named the way it is, because it has a yield strength of 36 KSI. So we've got 36 times 10 to the 3 there, divided by the safety factor, which is what we're looking for, is NAB 14.6 times 10 to the 3 pounds, changing kip into pound here, divided by cross-sectional area of AB, that's pi over 4, 7/8 of an inch is what we said the diameter was, squared. Okay, and then we get a safety factor out of that. So the safety factor for that, when you do it, comes out to be 1.48. Okay, so at this point here, because this has come out to below 2.0, we don't have to go any further with the problem. We can just say that because this is below 2, therefore not safe. Right? And that answers the problem. Right? Because that safety factor is below 2.0, it's not safe. Now, we could, of course, check and see, just for interest, what the safety factor of the aluminum cable comes out to be. And if you were doing that, right, you could write the following. So let's check the safety factor for CD as well here. So in this case, we're doing the yield strength for the aluminum divided by its safety factor is the normal force in the aluminum, which was cable CD divided by the cross-sectional area of CD. So that would give us the following. So the yield strength of the aluminum, let's see what that was. Okay. Hey, can you mute your microphone? Hey, hello, mute your microphone. Okay. Sorry about that, everybody. So let's do this. So what was I can't even think about what I was doing now. So we want the yield strength for the 2014 T6 aluminum. That's 60 KSI. Okay, so we've got 60 times 10 to the 3 here, divided by the safety factor is NCD 9.3 times 10 to the 3 divided by pi over 4/7/8 inch squared. Okay. And what did I get when I calculated the safety factor of that? Did I even calculate the safety factor for that? No, I didn't bother doing it because I reached this point and then I left it at that. So let's just do a quick solve on that and see. So 60 times 10 to the 3 divided by x equals 9.3 times 10 to the 3 times 4 divided by pi times 7 divided by 8 squared. Solve for x gives us 3.88. Okay, so you can see that the aluminum cable is safe, but the steel cable is not. Okay, and that again, even though the aluminum cable is quite a bit stronger, the steel cable ends up taking more of the load because it's got a greater stiffness than the aluminum. So we substituted one cable out with something else that was stronger, but the key thing here is that the actual modulus of elasticity wasn't paid attention to. The steel cable is much stiffer than the aluminum cable, so the steel cable ends up taking a greater proportion of the load than it would have if both cables were steel. Okay. All right, anybody have any questions about that problem? So you should be well set up now to do the questions that are in the second problem set, which is up on Brightspace now and due next Wednesday morning. So go for that. Okay, I'm gonna just stick around for a couple of minutes while people sign off. But for the rest of you who are leaving or who have already left, have a great day, have a great week. I'll post this after it all gets encoded here, and it'll be up for you to take a second look at or flip through parts of it as you need. You are most welcome. You guys are so kind. Let's do it again next Wednesday, shall we? The quiz, is it up on Brightspace and when does it due? Yes, it is up on Brightspace. It's due by tomorrow at 10 a.m. So it became available this morning at 10 a.m. and its due date is tomorrow at 10 a.m. So you can do it anytime that you want tomorrow before 10 a.m. Once you start doing it, you have 20 minutes to finish it and you can't pause. So pick a time when you're ready and that you have 20 minutes. No problem. For the lab, are our tests just the questions from tutorial 1? No. So for the lab, the different tests that were run are the individual samples that were run and that you've got the data for. So I think like you've got 3 text files that are included with the lab 1 data, one for like sample 1, one for sample 2, one for sample 3. So the mechanical test that was done on sample 1 is the data that is in the file labeled sample 1. So you would have seen in the video like the first test that the first mechanical test that was done, the data captured from that test is in the text file labeled sample 1. Yeah. Yes, I can. Yep. So there's a video. There's a link to a lab video that's being posted now too. So watch the lab 1 video, and then after you watch the lab 1 video, then read through the template, the Word document, and just follow what the instructions ask you to do. Watch the lab 1 video. You can ignore it for now because you're not doing lab 2 and lab 3 yet. Yep, no problem. Where are these videos for the lab? They're in the section of the Brightspace content labeled labs. And there will be links in there now to lab 1, lab 2, and lab 3. The question that asked, it covers up to lecture 4, yeah? What was that in reference to? The quiz, which, today's quiz? No. I'll write, so, let me, So, quiz number X is on the material that was covered in tutorial X, always. So if the X is 1, then quiz number 1 is on the material that was from tutorial 1. And if you look on the target schedule, the material that was covered in tutorial 1 was lectures 1 and 2. Okay, so when we're at quiz number 4 will be on the material that was covered in tutorial number 4, and the target schedule will tell you what the lectures were for tutorial 4. So you can always the numbers will always match up, and you can refer to the target schedule to figure out what the exact content is for the quiz. Yeah, exactly, because I want you to have the opportunity to work on the problem sets and really understand the material before you undertake those online quizzes. Yep, no problem. When will we be ready to do lab 1? You're ready to do lab 1. Go for it. You're ready. I believe in you. You're ready. Yep, absolutely. University, one of the key things that you learn is time management. You should always be looking ahead, seeing what you have due coming up in the next week, in the next month, and budgeting your time between schoolwork, part-time work, personal life, exercise, eating, leisure, all of those things. It's a key learning from university. Yep, excellent. Okay, I'm going to sign off now, guys. Everybody have a great week, and I'll catch you next week.